Okay, so just a quick comment on the exam. It is, the average is less than last exam. And that, considering everybody got, in addition to the bonus question, all of you got a +5 for the protein draft for the essay. So otherwise, you would have seen this averaging at least 5 points less. So, if you are around the average or higher, you're good. If you're down here, please go. Maybe we should sit down and talk because I'm worried about few of you for the final. Okay. Oops, no. So we left off here last time. Let's quickly finish the protein characterization and move on to vitamins lecture today. We were here and we talked a little bit about the nutritional quality of the protein in terms of determining essential amino acids, and specifically the first limiting amino acid, which is the essential amino acid that are present in the least amount compared to other essential amino acids. We talked about digestibility. Do you remember what we said about what would make a protein less digestible? Yes, Bill?
It's polymerized in other proteins.
So if we have polymerization due to processing, and then you wind up with large polymer, it would be hard for the enzymes to reach binding sites and digest that protein. Digestibility, on the other hand, is also enhanced if the protein is slightly denatured. Because if you have a really globular protein, we said, it will also be hard to digest it. So you want some partial denaturation, it's helpful, but full denaturation and polymerization actually has a counter effect. Proteins can also be anti-nutritional factors, such as enzyme inhibitors. There are specific proteins that inhibit enzymes like, can you give an example of a very common one? Trypsin inhibitor. So the trypsin inhibitor is very common in soy, and that's why there are regulations how you process soy-based products to ensure more than 90% inactivation of trypsin inhibitor. If it is not inactivated, you'll consume it and you won't be able to digest your protein adequately because of them inhibiting trypsin. Lectins are also a form of protein present in beans, and if you eat a lot of raw beans, the raw beans would contain significant amount of lectins that would cause inflammation in the intestinal tract. So these are anti-nutritive factors. Okay, so how do we determine amino acids? So basically, if you want to determine the composition of amino acid, you want to break down your protein into their amino acid building blocks. So you want to hydrolyze the protein all the way to single amino acids. So you want to break every single peptide bond, basically. And the way you do it is you use strong or concentrated HCl. 6-normal HCl is commonly used. And you apply heat, and you do that over an extended period of time. On average, it's actually a lengthy period of time of 24 hours. And then you get your amino acid. But under this process, you can denature, or not denature, degrade certain amino acids. For example, tryptophan is completely degraded by acid treatment. So if you want to quantify tryptophan, you want to do alkali hydrolysis to quantify tryptophan. There are other amino acids like serine and threonine. They also are degraded over time. So samples are pulled at different times, and then a factor is produced, and you can calculate the loss in serine and threonine. So there are ways around getting an exact amino acid composition, but the analysis requires different steps, procedures. But anyway, once the protein is hydrolyzed into individual amino acids, then you quantify the amino acids by chromatography. So most common, you either use ion exchange chromatography or reverse phase chromatography. You cannot directly determine or measure these amino acids by UV. Why is that? Why can't we use UV? You can use UV for proteins, can't you? Yeah, why not for individual amino acids? Sarah?
Now amino acids can absorb.
Exactly. Not all amino acids can absorb light. So a protein, all proteins have a certain composition of tryptophan, tyrosine, and phenylalanine. These are the three amino acids that absorb UV light. So all proteins, to a certain extent, have these three amino acids in them. That's why you can measure absorbance. But you have 17 or 18 other proteins, amino acids, that do not absorb UV light. So in order to quantify all of them, you have to chemically change them into a chromophore. And there are several ways of doing that. One common one is ninhydrin. And oftentimes it's a post-column derivatization. That means you have your separation and then there is a chamber where the reaction occurs, and then you can measure absorbance at 570 visible range. If you do the phenylthiocarbamyl, you can then measure at UV, under UV absorption. Or if you do OPA, you will end up measuring fluorescence. You can measure absorbance at 340, but oftentimes you do excitation at 340 and then you measure fluorescence at a longer wavelength. That's more sensitive for amino acid composition. And a side note here, OPA is a very commonly used method to determine degree of hydrolysis. And that means how many peptides have been broken from the total amount of peptides. So if you're producing a protein hydrolysis, and you want to determine the extent of hydrolysis, it's based on OPA reacting with the amine group. So the OPA reacts with the amine group, gives you a chromophore, and you measure that. The more peptides you break, the more amine groups are available to react with OPA. If all peptides are broken, all amino acids will react because all of them will have a free amine group to react with. Okay. So protein quality is not only limited to amino acids. There are also, as we said, the factor is protein digestibility. So a very common procedure to determine protein quality is the protein digestibility corrected amino acid score. It's a mouthful. PDCAS. Okay, so the PDCAS takes into account two criteria. The first limiting amino acid and the digestibility of the protein. So basically you have to determine the amount of the first limiting amino acid you have in your protein, and you calculate an amino acid score relative to a reference protein. And usually you select a protein that has a complete, or it's a complete protein, that means it has all the essential amino acids. Common one is casein. So casein is commonly used as your reference protein, and you get a score. How many milligrams of the first limiting amino acid in 1 gram of test protein versus 1 gram of reference protein. So you get that first one. The second component is doing a digestibility assay. And usually this is an in vivo assay. So rats are involved in the process. So you give them a diet with 10% protein, and then you do a bioassay to determine how much nitrogen was absorbed. The more the protein is digestible, the more nitrogen will be absorbed, obviously. So you get the true digestibility, which is the nitrogen absorbed over the nitrogen intake, and you multiply that by 100, it's a percentage, and then you get a PDCAS score, which is a multiplication of this relative number with the percent true digestibility. PDCAS of 1 is a maximum score, that would be a high quality protein. So any protein, PDCAS 1 is a very good quality protein, and anything less than 1 is relatively less quality. And the PDCAS is influenced not just by the type of the protein, by the processing as well. So even if you start off with a really good PDCAS for a particular protein, if you process it and you have adverse processing conditions, then the PDCAS will be affected. So you always need to know what the PDCAS is for the final protein that is consumed by the consumer, basically. And then you get that PDCAS score, and then you use it to get the percent daily value. So you have the recommended daily value for protein is 50 grams per day. And then you get how much grams you have of protein per serving. You multiply it by the PDCAS value. And then this number is actually multiplied by 100 here. So make sure you add that. It's a percentage. So basically, if you have less than 1, your percent daily value will be less than 100. Okay? Protein efficiency ratio is mostly applied for infant products. Why? Because of the type of the assay. Type of the assay is based on rats, but in this case, baby rats. So these baby rats they consume a certain amount of protein, and they measure growth in weight. So total weight gain over a period of time by the amount of protein that is being consumed, and you get a protein efficiency ratio. So for example, casein has a protein efficiency ratio of 2.5. So if your test protein is 2.5 and your PER of casein, which is your reference protein, is PER, is 2.5, then you get the corrected PER again 1. Corrected PER maximum score is 1, basically. And why is this relevant only to infant formula? Because infants' rate of growth is similar to the baby rat rate of growth. So you can relate those. But for adults, this is not possible because we don't grow every time we eat proteins. So hopefully not. So that's why it's not relevant for children and adults. Okay, other tests, just a list of them. Other tests may include just determining an index for all of the essential amino acids. So you calculate, there's a calculation or an equation to get the amino acid index for all the essential amino acid in the food. And then you have in vitro protein digestibility. If you're not always able to have an in vivo assay, you can have an approximation. So if you're looking at different modification of the protein or processing, and you want to see relative to the native protein or the original food, what happened to the digestibility, you can do in vitro assay. And an in vitro assay, basically you subject the protein or the food to digestion by a gastric enzyme. So you use, in sequence, you use pepsin and then trypsin, chymotrypsin. So a series of intestinal enzymes. Some add bile, similar bile, that aid in the digestion. So, and then you get an estimated protein digestibility. There are a couple of methods that you would use to calculate percent digestibility. You can use pH shift method, and that means you start off at a particular pH, and then the pH drops over time. Why does the pH drop? Why do you think? You said something. What happened to the protein when it gets digested? What gets released? Free amine groups, but at the same time, what? carboxyl groups that gives protons. Yes. So you will have acidity. So the pH will decrease. So at the end of the digestion, you measure pH, and then you use it in an equation to calculate protein digestibility. pH stat method is where you actually keep the pH static, means constant. So what you do in that case, you keep adding NaOH, monitor the pH, and keep adding NaOH to neutralize it, bring it back to where it was. And then at the end, you get a volume of the NaOH used, and you have the normality, and you use that in the equation, and you get the digestibility that way. Other methods are basically chromatography methods, so you can look at protein and peptide profile and get changes in the peptide profile over time to determine how much of the protein get digested. Last one is lysine availability. Lysine is an essential amino acid and commonly lost during processing a lot. Why do you think that? Why lysine specifically is susceptible to processing loss? You know this from your food chemistry. Sarah? It participates in the Maillard reaction. That is right. So it's the most susceptible amino acid because of its extra secondary amine that is present, and it reacts more readily with your reducing sugar. So during processing, this would be the first amino acid to be lost, and it happens to be an essential amino acid. So there are ways of quantifying it, mostly reacting it with a compound that will give a color, and you can determine absorbance. That's most common. Other more elaborate methods involves HPLC, and one of them is furescine assay, which is not listed here, but anyway, there are different methods for determining that. Last, your book chapter talk about protein functionality. It's part of characterizing the protein. So proteins are used in industry for different applications, and they are used in beverages for their solubility. They are used in meat products for their emulsification properties. They are used for foaming in creams and ice creams and cakes and stuff like that requires foaming, and they are used for their gelation power in, for example, tofu, meat imitation products, and of course the gluten for their dough forming property, wheat protein. So, but in this class we're not going to go over any of these. However, in chemical reaction you're going to have a lab on that, and you'll do functional determinations of proteins. That's that. Any questions on proteins? I feel the excitement in the air. Or not. Okay, moving on.
You might boost the morale in the room if you gave 5 points or something. Throwing out.
What's the attendance status? Who are we missing? People we like, people we don't like?
It depends on the amount of chocolate they give us.
Huh? We're missing 3 people?
Yeah. Based on trust.
Let me dwell over it for a little bit. I want to see if these people are regularly attending class and they happen to miss today, or they're commonly missing class. We will determine at the end and announce later. Okay. Vitamin analysis. Did you notice how this class is all over the place in terms of topics? Yeah. That means it's very fruitful. It's a good thing. Huh? You learn everything. Every single thing in food science and nutrition, you learn how to analyze it here. Yeah, great. Okay, vitamins. What is a vitamin? There is a common mistake that often students confuse with another component of food. And I can tell you right now, when you ash a sample, what remains in the ash? What about vitamins? No. Common, very common mistake. Students think that the ash is vitamins and minerals. No. Ash is organic. It's going to combust. All right, so what's the definition of vitamin? Now that we established that.
An organic compound that is required to be consumed for proper health.
It is required, and vitamin is, I think is it in Latin or in Greek that it means crucial or essential? Latin. So it is required because the body, whether it's a bacteria or it's a human body or an animal body, require vitamin for growth, for different physiological functions. And we don't produce it in enough amounts. Some of them we don't produce at all. So we need them from an external source. That's what vitamin is. And what is it, why is it important to analyze vitamins?
Deficiency?
Yes, so we need to know how adequate the food intake we are taking in terms of preventing deficiency in these vitamins. Very good. What else? Yes.
Taking too much.
Which vitamins we shouldn't take too much of? Huh? Fat-soluble ones. If you take a lot, they become at a toxic level. Good. So from a nutritional perspective, deficiency and toxicity, we need to measure them. Other than that, always, it's part of everything. Huh? They took your answer, Drew? Or you were going to say?
Chemically and react with food components.
Yes. So degradation. So degradation during processing. We might lose these vitamins, and therefore we need to monitor the effect of processing on that. Some of the vitamins are very heat labile, some are prone to oxidation, some are very susceptible to degradation because of light. So it's very essential to see what happened to our vitamins before they reach us as consumers. So here they are. So you can get that definition, you don't have to write it down, you already know it. And these are what we talked about. We talked about diet adequacy for deficiency. Another one was the toxicity, it's not there. The nutrition label, and determine the effect of processing. So what vitamins, or which vitamins used to be on the label, or are still on the label right now? Yeah? A and C, right? What did you say? A and C? Okay. Now what? Just D. They dropped the A, they dropped the C. It's just D. Due again to the deficiency in D specifically. In the past, when it became a nutrition requirement, there were a lot of deficiencies in A and C, and that became a requirement for nutrition label. Nowadays, it's not the problem. The problem is vitamin D, which makes it stinks for our lab next week. Well, we're measuring vitamin C next week in the lab, and it's probably the last year we do that. So sad. It's a very fun lab. The reason we used to do that, what you're going to do next week, actually look at the impact of different processing on vitamin C, and vitamin C is the most heat labile vitamin. So in addition to having it being important for the nutrition label, also it's important that manufacturers account for any degradation that might occur to thermal processing and shelf life, during shelf life. and make sure that whatever remains at the end of shelf life does not go below 80% of, if it was not added, if it was like an orange juice is present naturally, they want to make sure it doesn't go below 80% of their claim. So it was a very cool lab. It is still cool. You're going to have it next week. We still have vitamin C on the labels currently on orange juices, but probably next year they will be gone. So with that, sadly, we will cancel vitamin C, but we might have vitamin D instead, which is not as fun. Anyway, so we already asked that question. Your old nutrition label had A and C and still has this year. But sometimes they fortify with vitamins. So they choose to list all of the vitamins and minerals in this case that they have fortified their product. So they will have to, for the nutrition label, also quantify the other vitamins if they are making a claim as a source of certain vitamins. And this is, again, to restate what we talked about. Now it's going to be vitamin D from next year on. This is a very important table, not for you to memorize now, but for College Bowl. Seriously, but I don't see College Bowl participant. Somebody was, and it's not showing up anymore. But, okay, but this is really cool table. It is common knowledge, general knowledge. You have water-soluble vitamins. You need to know the water-soluble versus the non-water soluble and the fat-soluble. And the common way to remember is EDIC. I don't know if you have that abbreviation before, ADEK. And then vitamin C, vitamin B, you have multiple vitamin B. You have the thiamine, riboflavin, and niacin, biotin, folic acid. So B12, I'm not going to say the name. Yeah, so there are a lot of different B vitamins and different sources of them and the year that they were discovered. Very good College Bowl. Again, stressing College Bowl. Okay, so vitamins. They all are vitamins, but they have nothing in common in terms of structure. So they are very, very different in structure. Some vitamin E, for example, has a phenol group, a hydrocarbon chain. This vitamin 9, folic acid, has nitrogen in it, and especially has glutamic acid, which is an amino acid. So some don't have nitrogen, some have just ring structure. Some are bigger than others. So like you see here, they're very, very different. They're all small molecular weight, so they're not like huge compounds, but they're very different structurally. Because of that, is it possible to analyze all vitamins following one technique? No. Not at all. Should we give +5 now?
Yes.
No. Or take it away? Okay. So no, there are so many different methods, and each vitamin requires their own method of analysis. So analytical methods vary. So you have bioassays, which are in vivo assays. Most commonly, the two vitamins that are used, or that we use bioassays for, are vitamin D and vitamin B12. But oftentimes, for example, vitamin D can be analyzed by LC methods, and there are official methods for LC determination. There are microbiological assays where we look at the growth of microbes that require vitamins for growth. So that would be niacin and folate. measure the growth of microbes at different concentrations. So you can create a standard curve and then measure an unknown sample, and then you can determine the quantity in an unknown sample. And then you have the chemical assays, where some are based on titration, other based on chromatography, and all require extraction first from the food matrix. So in your textbook, chapter 11, there's a table that summarizes the common official methods used for vitamin analysis. Like I said, all of them require that you extract them from the food matrix in order to apply or analyze them. So because they differ in solubility, some are water soluble, some are fat soluble. The water-soluble vitamins commonly require either acid or alkali extraction, and some of them, like thiamine and riboflavin, require heat, retorting, very high temperature. So the fat-soluble vitamins, they require essentially a step called saponification, like you're very familiar with it right now, because you want to saponify the fat so that you release them from the fat and have a phase separation. So you make sure you produce soap, the fatty acids so you saponify with KOH and you produce soluble fatty acids, and then you will extract the fat-soluble vitamins with an organic solvent. So this is a very common procedure before you quantify them. Enzymes, some of them require enzyme treatment, like folic acid, for example, and we'll talk about why folic acid, for example, require pre-enzyme treatment before analysis. Precautions. So many of these vitamins, like I highlighted here, actually, they are sensitive to pH, light, oxygen, and temperature. For example, vitamin C is very sensitive to alkaline pH. It would get degraded under alkaline pH. So you'll see that your assay have an acid component of it, where you reduce the pH to prevent degradation. Some are light sensitive, like riboflavin and vitamin A, for example. So you want to make sure when you analyze for those, you analyze under subdued light. Others are prone to oxidation. Vitamin E, vitamin C are prone to oxidation. Folate is prone to oxidation. Others are very sensitive to temperature, like vitamin C, our most labile vitamin, heat labile vitamin. So there should be precautions for when you are doing the analysis. So for example, if you are trying to analyze a product that is very prone to oxidation, you can either make sure you flush with nitrogen, make sure you don't expose it to a lot of oxygen, or the analysis time is short, so you don't worry about oxidation. Otherwise, you need to add reducing agent or antioxidants, same thing, antioxidant reducing agent, such as beta-mercaptoethanol. And this is very important for those that are really susceptible to oxidation, such as these examples here. And we said flush with nitrogen is another way to prevent oxidation. Chelating agent, this is very important, especially for vitamin C. If you know that your sample contains a lot of copper or iron, so they are susceptible to oxidation in presence of these metals. So you would add chelating agent to make sure that your vitamin C does not get degraded in the process of analyzing the sample. This is actually something that happened to a Capstone group. So they were producing this product and they were fortifying their product with vitamin C and a lot of minerals, including iron. And they wanted to determine, after processing, how much leftover of vitamin they ended up with. And they were using the method you're going to use next week in the lab to determine vitamin C. And they wouldn't find even 10% of the vitamin C in their product. They got very concerned and they were talking to me about it, and I said, you have a lot of iron. Yes? Did you use EDTA? No? Okay, that's what you need to do. So they went back, used EDTA, and they found, voila, all of the vitamin C in their sample showed up. Okay, we talked about controlling the pH, subdued light, and make sure we don't subject our sample to heat while we're analyzing. I'm going to skip over bioassays, microbiological assay, and go to vitamin C because that's your lab next week. If we don't have time today, I'll go back to those assays on Monday. But let me make sure I go over vitamin C principle because it's relevant to the lab. So vitamin C is a chemical analysis, is a chemical method analysis. So in here, the principle of the method that you're going to be using next week, it's based on ascorbic acid reducing a dye. The dye that you're going to work with is a dichloroindrophenol dye. And you acidify your sample, make sure you have enough acid in there to lower the pH. And then what happens is your dye that is oxidized at the beginning has a color. So it's going to be dark purpley color. L-ascorbic acid is reducing and the dye is oxidizing. So the dye is going to oxidize the ascorbic acid and generate aldehydoascorbic acid. And so you wind up with an oxidized ascorbic acid and a reduced dye. The reduced dye is colorless. So it's a titration reaction, so you're going to mix your dichloroindrophenol or titrate with dichloroindrophenol, and every drop you're going to add to your sample is going to be reduced and no color. Okay, so the color of the dye will disappear as soon as it hits your orange juice that has ascorbic acid until all ascorbic acid gets oxidized to aldehydoascorbic acid. The last drop that you're going to add will turn your solution color. And in this case, you'll see a very faint pink color. And we use the volume of the dye to calculate the amount of vitamin C. We'll use a vitamin C standard to determine, to follow a certain equation. You'll be introduced to it next week in the lab. This procedure only measures L-ascorbic acid. This is important to note because sometimes your orange juice, let's say on the shelf, is in a container that might have oxygen in the headspace of that container. Some of your ascorbic acid will be oxidized in that container to aldehydoascorbic acid, which is the initial form of oxidized ascorbic acid. It's still bioavailable. It's still not considered degraded. So, however, if the oxidation proceeds, more oxygen, more light, and more heat, you're going to wind up degrading the vitamin C. But some of your vitamin C in your juice will be in the aldehydoascorbic acid and still a bioavailable vitamin C. So if you have some of that in your sample, using this method as is, you won't be able to quantify the aldehydoascorbic acid because aldehydoascorbic acid cannot reduce the dye, so you won't be able to detect them. Okay, if your product is not orange juice, if your product is grape juice, how would you can't see the color change. What would you do in this case? When indicator does not work, no, this is not titratable acidity, so we're not looking at the change of a pH. There's a color change. So when there's a color change, measure absorbance. Spectrophotometrically, we monitor reaction using a spectrophotometer at a particular wavelength. Okay, so here's the chemical reaction. So basically you have your ascorbic acid, which is colorless. You have, oh, it's not really red. You'll see it in the lab. It's really dark, purpley colored. So this is the oxidized form of the dye, so it will have a color. And then when the ascorbic acid reduces it, this becomes colorless. So that's the principal reaction. So I did tell you that we cannot measure aldehydoascorbic acid. But if we insist and we say we're going to use this method and determine everything, the oxidized and non-oxidized form, how can we do that? There is a way, a very simple way.
Can you add a reducing agent?
Yes, we can add a reducing agent, definitely. So you run the assay without a reducing agent, you get the amount of non-oxidized L-ascorbic acid. Then you run the assay again with not EDTA, with beta-mercaptoethanol, for example, or DTT, and then you can bring whatever has been originally as aldehydoascorbic acid, bring it back to L-ascorbic acid, and you do the titration. You'll get the total amount of vitamin C in both forms, and you have the one that was not oxidized. If you subtract both, you get the amount that was already oxidized. Okay? So with and without, you will be able to determine the different forms in your sample. So that's basically what you're going to do next week. You will be doing this in different types of orange juice. Fresh, you're going to squeeze fresh orange juice from an orange, and you're going to get a frozen concentrate of orange juice, and you're going to get orange juice that has been pasteurized and in the fridge, from the fridge. So pasteurized, freezed, in cans, and fresh orange juice. Another method to determine vitamin C that is an official method for all types of foods is a microfluorometric method. And in this case, you oxidize. You start with oxidizing L-ascorbic acid to L-dehydroascorbic acid. So you are quantifying in this assay L-dehydroascorbic acid. And you react with O-phenylenediamine to form a fluorescent, and then you measure the fluorescence, basically. You would have standards, and you get a calibration curve, and you measure your ascorbic acid, and this measures both forms, the total amount. But if I want to differentiate between originally what my sample had as L-dehydroascorbic acid versus regular ascorbic acid, how can I do that? This assay is going to measure the total. If I just want to know how much I had originally non-oxidized versus oxidized, simple. Take out the oxidation step. So you run the assay without oxidizing, so you will get only the original, whatever in the sample has been in this form. And then you run it with oxidizing, and the difference will be whatever you started off as L-ascorbic acid. Okay? All right. So with that, I'm going to go back to bioassays. We have 5 minutes. Let's see what we can finish. Okay, so bioassays, like I said, are in vivo assay using animal models. And the only two vitamins that can be analyzed this way is vitamin B12 and vitamin D. So it involves animals and sacrificing them to quantify. So the very common test for vitamin D is line test, and it's an official AOAC method, mostly for infant foods. Well, I take that back. Not mostly for infant food. For all sorts of food, you can do that. Okay, so the line test is basically based on calcification of the bones. So, because vitamin D is important for calcification of the bones, so this is how they do it. They start off with a set of animals, and they have a period of depletion, meaning they deplete the vitamin D from their diet. So they bring it down to 0 deficiency, 100% deficient in vitamin D. And then they feed them diets with different levels of vitamin D to generate a kind of a standard curve. So each set of animals will get one concentration, one known concentration, and then you have another set of animals that will get an unknown concentration of vitamin D, or your food that you want to determine your vitamin D composition. And then sacrifice the animal, get a particular bone, and they measure the calcification of that bone. And they generate a calibration curve based on the calcification of the bone at different concentration of vitamin D. A very laborious experiment, and of course it involves sacrificing animals. So now mostly it's not used, mostly is the HPLC method for vitamin D that is used, require specific steps to extract the vitamin D, and then use normal phase chromatography for quantification. Microbial assays, like I said, involve the growth of microbes that require particular vitamins for growth. This is very common for niacin and folate, or folic acid, vitamin 9, I think it is, yeah, B9. So in this case, you have a growing media, or the growth media, and then you measure, you generate a standard curve. So every growth media gets a certain concentration of vitamin D, and then one growth media gets whatever vitamin D, unknown vitamin, not D, sorry, folate, or whatever vitamin we're measuring. The unknown, huh? Did anybody say anything? Ah, my ears then. Okay, so, and then you measure turbidity is a very common way of measuring growth. So the more vitamin D, why am I insisting on vitamin D? The more vitamin you have, whether niacin or folate, you'll end up with higher turbidity. You can also measure acid production or gravimetry by measuring how much the mass of these microbial cells at the end, or respiration, how much oxygen is being consumed. But most common, it is turbidity measurement. So for folate in particular, so a certain microbe is used, bacteria, and then here's your folic acid. But oftentimes you have multiple glutamate in a series, so it will be a very long chain. So in order to quantify, you have to break down the glutamate chain. So in order to do that, you need to use enzymes, but prior to using the conjugates, which actually breaks down the glutamate, you use alpha amylase and protease, because in your food, your vitamins could be entrapped in starch and protein. So you want to release them from starch and protein, so you hydrolyze with amylase, protease, and then you add conjugates to break down the glutamate. So they call it a tri-enzyme digestion method. It's an AOAC method because it involves 3 enzymes. And then you take that extract after you hydrolyze, and then you use it in the growth media, and then you measure turbidity by measuring transmittance at 550 nanometer. Chemical methods, which we talked about vitamin C as being chemical method, but also measuring vitamin A, E, and D are measured via chemical methods. But since they are fat soluble, they require the saponification and the solvent extraction. And like I said, saponification with KOH is important so that you solubilize the fat, so break down triglycerides, solubilize the free fatty acid, get them into the aqueous phase, and then you use solvent to get the vitamins into the organic solvent. And there are certain procedures, there are figures in your textbook for the detailed procedure, but you use LC, all of them, normal phase. Some require UV detection, others fluorescence detection. Talked about this. The last one is this, but since we ran out of time, we will go over it on Monday. Quiz is on Monday, just a reminder. And does not include this lecture. Did you hear me? No? Shh. The quiz on Monday include vitamin C. No.
What you just said.
I just said no vitamin lecture on Monday.
All we talked about was
Protein and fat.